Welcome back, ladies and gentlemen. So, today we're going to start talking about probably one of the biggest organs in the sense of its importance, at least in your body, and that's your heart. So, we're going to focus again on the human heart, just because we're going to give you that sense, give you that exposure of what's going on in your own body. So, when we look at the heart, just to kind of give you a definition here, right? It's a four-chambered muscular organ. It's located in your chest and it sits between your lungs just slightly to the left. And its major function is to pump the blood that it receives from the veins that are coming back from your body into the arteries that will then go feed your body again. And so they continually maintain the flow of blood throughout your entire circulatory system. So if we look right here is where your heart sits. All right, your lungs are on either side, okay? And if you look in terms of a top-down version, right, it's definitely anterior towards the front of your body. Here's your spinal cord in the back, all right, and it's nestled between your lungs. So just some kind of tidbits of information here, right? It is slightly larger than a clenched fist, so actually clench your fist, all right? And that gives you a basic idea of approximately how large your heart is, all right? And again, it does sit between your lungs. It sits behind your sternum, which is the connection between your rib cage, right, in the center of your body. It is for sure one of the strongest muscles in the human body. It is made mostly of involuntary muscle tissue called your cardiac muscle. Um, and it's involuntary in the sense that don't have to sit there and think about telling your heart to beat, which is really important. Because if you had to sit there and constantly tell your heart, hey, beat, hey, beat, hey, beat, you end up skipping beats all over the place. You wouldn't have a regular heartbeat. And then what happens when you go to sleep, right? So it's really important that that muscle is involuntary. Your brain just kind of takes over the function and does what it needs to do. Um, it beats somewhere on the order for most people about 75 to 80 times a minute. All right, at a resting heart rate, that's kind of an average for most adults. Um, some adults run a little high, some adults run a little low. You go into children, that heart rate goes up. But that's approximate for most people. So think about that though. It is over 100,000 times a day that it's beating. No wonder it's one of the strongest muscles. Here's a challenge for you. If you have a tennis ball sitting around somewhere, pick that tennis ball up, put it in your hand, and try squeezing it as many times as you can in a minute. Try to hit that 75 to 80 times a minute, and you are going to see just how tired the muscles in your hands and your forearm get. It's almost impossible for most people to be able to maintain that for any real length of time. And that'll give you just a sense of how much work your heart muscles are doing for you all the time. So, if we take a look at some of the anatomy of your heart, the actual heart wall itself is split into three layers. You've got your epicardium, your myocardium, and then your endocardium, and just kind of think of what those prefixes mean. Epi is above, right? So your epicardium sits on the outside of your heart. That's the furthest layer out. Your myocardium, myo means muscle, so that is here, that is the muscle layer on the inside. And then your endocardium is the innermost layer, and that's going to be right next to where all that blood flow is happening. Okay. There's serous membranes. All right. So what does that mean? Especially your epicardium there, is that it's capable of producing fluid, and that's a good thing so long as it's being done in the appropriate volumes. So the epicardium will make a serous fluid, a pericardial fluid that surrounds your heart. And the whole point to that is that as that cardiac muscle, that myocardium layer is beating and contracting, we need that fluid there to reduce the friction between the heart itself and the rest of your thoracic cavity, your chest cavity. Um, because if we didn't, we'd be sloshing off cells all the time, and that's not a good thing. We'd constantly have to be replacing them. So the whole point to your epicardium is to make that pericardial fluid to reduce the friction, all right, to allow your heart to beat and beat smoothly without um, roughing the edges, if you will. That being said, there are certain situations where you can build up too much pericardial fluid, and that's not good. And if you produce that excess pericardial fluid and have no way to get rid of it, it can actually cause your heart to arrest, stop your heart, until that fluid is released. So, in a good working functional heart, everything going well, it does a really nice job to reduce that friction, but on occasions it can become a problem if too much fluid builds up there. Your endocardium is your inner layer, right? And that's just going to maintain that epithelial layer so that that fluid flows freely. It does also stretch into your great vessels, which includes your aorta going out to your systemic circuit, as well as your vena cava coming back from your systemic circuit. All right, so this is just another way to take a look at those layers, right? So here is your pericardium, right? And this is connected to your lung tissue, right? Your pericardial cavity then is sitting here in the middle. Your epicardium includes this loose connective tissue here, which will produce the fluid to maintain that pericardial function so that we're not um, rubbing up against this, right? Your pericardial sac is the sac that your heart sits in, and we want to be able to maintain a minimal friction layer there, so that's where your epicardium comes in. Your myocardium is this huge chunk here in the center, right? Mostly that cardiac muscle cell. And then your endocardium here is a little more connective tissue and endothelial cells here that line the inside of your heart. So let's talk about cardiac muscle for a second and connect this back to your cell structure. These are muscle cells, means that they're beating a lot, which means they need a lot of energy. And so when we look at these guys, here's a type of cell that you would expect to have incredibly large amounts of mitochondria, and they do. Because they need to do all that cellular respiration in order to be able to make all of that ATP. That does mean that they have a high dependence on oxygen. So, not getting oxygen to that muscle tissue is a really, really big problem. Um, so, think about things like heart attacks, blood clots, and things like that that occur in your heart. If we're not feeding your heart muscle with oxygen, these cells start to die pretty quickly. And that can lead to some pretty intense damage to the heart tissue, which is a problem. They utilize a variety of other nutrients as well, so it's not just oxygen, um, but that's certainly the big one. They are composed of both autorhythmic cells, right, and contractile cells. So again, being able to maintain the actual function of your heart in the sense of just contracting, but then also being able to maintain your heart rhythm. So we'll talk a little bit in the next video about your autorhythmic cells and how they actually are able to maintain your heartbeat and your heart rhythm, which is also very important. Um, some things that come into play in order to keep those cells to being able to do their function beyond just the mitochondria and their dependence on that oxygen. You also have a lot of uh, pumps in here, sodium pumps, potassium pumps. So your sodium potassium pump itself is also really important. Calcium channels as well to be able to maintain those electrical potentials. So we need to be able to keep those membrane potentials at a certain level so that we are able to make those heart beats consistent. So if you've ever heard of somebody who has a pacemaker, they have some artificial material in their body to be able to maintain those cell rhythms, but you have a natural pacemaker. And those autorhythmic cells use the exchange of things like those sodium, potassium, and calcium ions from the internal and external pieces of your cells to be able to keep those potentials where they need them to be so that we can switch them quickly and be able to send signals, just like your nerve cells do, which is pretty cool. So if we take a look just at the exterior anatomy of your heart, again, don't get lost in all of this, but just some of the ones you probably should be familiar with. Certainly where your connections to your aorta and your aortic arch are. Um, Your pulmonary veins and arteries stick out of the back here. Here feeds in your superior vena cava, bringing blood back from your head. Inferior vena cava, bringing it back from the rest of your body, your pulmonary veins, that kind of thing. You do have the blood vessels that actually supply your heart itself. So you've got your coronary arteries and coronary veins here. They talk about the point of your heart being the apex of your heart. So those are some pieces to be just kind of familiar with. And if we take a look at the back, you can also see some of those connections to where those veins leave out, where your arteries come back, your aorta, superior and inferior vena cava, where that feeds in. You do have this coronary sinus back here, which is going to be something I'll mention to you in terms of where that blood flow from your heart actually goes in order to feed all of these coronary arteries and veins. They're going to come from that coronary sinus back here. So again, just kind of looking at some of the major anatomical structures. Don't get lost in it, but the more you're familiarize yourself with it, just in basic anatomy as you can manage, just gives you some idea as to where things fit in. All right, so let's dive into your heart then. And there are definitely some components you want to know here. So again, it's a four-chambered heart. So you've got two aortas, two ventricles. Keep in mind when you look at the anatomy of a heart and what we label as right versus left is based off of the patient, right? So we're assuming medical system here. So we're talking about your right and your left when we're talking about your heart. So when you look at a diagram, it's essentially reversed. Hopefully that makes sense, right? So patient lying on the table in front of you, this is their left, this is their right, um, but it's opposite of your right and left hand facing them. So hopefully that makes sense. A couple other things I want you to kind of pick up here. Look at the difference in the thickness of the walls of the ventricles, right? These are going to be the ones that are responsible for the pumping, the pushing of the blood out of your heart. Atrias get filled up from wherever they're returning that blood from, and then the ventricles are the ones who push. Considerably less muscular on the right side of your heart, right ventricle, as opposed to the left. And just think about where this is going. So that right ventricle is going to be pushing blood out to your lungs, which really isn't a huge distance, um, comparatively speaking. Your left ventricle, on the other hand, has to maintain the pressure to the rest of your body. And so considerably more muscle on this side because it's pushing all of that blood out to your entire body as opposed to just your lungs. Okay, so we took a look at those chambers. You also have four valves that separate those chambers from each other, as well as valves that separate chambers from the major arteries of your body. And the whole point to these valves is to prevent the backflow of blood, right? We want to keep your circuit going in a single direction. So your atrioventricular valves, your AV valves, atrium, ventricle, ventricle, right? These guys are going to separate your atrium and your ventricle. And depending on how many sort of leaves or partitions there are, is where they get their names from. So your tricuspid valve has three components, and we'll look at what that looks like in a second. And then your bicuspid valve has two pieces, or you may also come across it as your mitral valve. Okay, so tricuspid valves here on this side of your heart, and your mitral or bicuspid valve is on the opposite side. Your semilunar valves, they kind of literally look like rounded half moons when you look at them, which is where the name comes from. But these guys then control the blood flow into your major arteries. So you've got your pulmonary valve that is going to keep blood moving out to your pulmonary circuit. So it's going to separate your right ventricle into those pulmonary arteries. And then your aortic valve is separating your aorta to your left ventricle. So here again, if you take a look, you can see what I'm talking about. So here are those semilunar valves. So they sort of look like little half moons, half circles when you look at them. They each have three flaps. And then your bicuspid valve has two components to it, so two flaps here, also known as your mitral valve. And your tricuspid has 1, 2, and 3. And so that's where those terms come from. And you can see if you cut the heart in half from top down, you can see those components there. If we take a look on the inside and just look at what's connecting them, so we cut the heart the opposite direction, you can see that there's all of these fibers that are connecting those valves to their components here. So all of these, what we call chordae tendineae, are tendons, literally. You ever hear somebody talk about, you're pulling on my heartstrings? This is where the saying comes from. Because those heartstrings, okay, those chordae tendineae, actually attach to the vessels, or excuse me, I should say the flaps of the valves in your tricuspid and bicuspid valves. And then they connect to this stuff called papillary muscle, which is what you're seeing here. So here are the cords. Your flaps of your valves are up here, and then your papillary muscle then connects to the rest of the wall of your heart. And this does weaken and break down over time. So you will get people who will have heart valve issues where they will get backflow of blood. If you've ever heard of somebody talk about heart murmurs, you can hear this if you know what you're listening for. It literally sounds like gurgling when you listen to somebody's heart pump. And the reason for that can be a multitude of things: diabetes, hypertension, just being overweight, or just getting older for that matter, will cause these cords to stretch out and this muscle to weaken over time. And that's where you'll get a lack of complete closure of those valves, and that's where that backflow can come from. Or at least it's one potential place that that backflow can come from. Okay, so let's talk about each of the chambers themselves. What's there, where's the blood going, what's it going through, so on and so forth. So we'll start up here in your right atrium, right? And so this is going to receive that deoxygenated or oxygen poor blood coming back from your body. So you've got 4 major openings here. You've got your superior vena cava, which is bringing blood back from your heart and your upper torso. You've got your inferior vena cava feeding into this as well. That's bringing blood back from your lower part of your body. You also have your coronary sinus back here. All right, so that's going to be bringing blood back directly from what's feeding your heart. And then you have the tricuspid valve that'll ultimately empty out into your right ventricle. Okay, moving along, we're now down into your right ventricle. This is going to be ultimately responsible for pumping that deoxygenated blood out to your lungs. So a couple of major anatomical things here. All right, here's that papillary muscle and the the papillary muscle and the chordae tendineae, I should say, that are connected to the flaps of your tricuspid valve, right, your heartstrings. Again, every time that your heart pumps, those papillary muscles contract, tense up that chordae tendineae, limiting their movement, preventing the backflow of blood. Everything relaxes and things snap back into place. All right, so the heart contraction really is what's pulling on or allowing the relaxation of those cords, and that's how you keep those valves opening or closing at the right times. And then you also have connection up into through that one of those semilunar valves, your pulmonary semilunar valve to be more specific, out into your pulmonary arteries, which will empty out either to your left or to your right, going to your right or left lungs. All right, come back, and now we return from the lungs and we look at your left atria. It is smaller than your right one, but has considerably thicker walls as a result, hence why the chamber itself is smaller. So it's going to return now oxygenated blood back from your lungs, all right, through your left and right pulmonary pulmonary veins, I should say. And then that will also dump through your bicuspid or your mitral valve down here. Again, as hearts contract, we open up those vessels because of the pulling of that papillary muscle and those chordae tendineae. Something I do want to mention here, just while I'm thinking about it, Whenever we have something come back to the heart, we talk about them as veins. Anytime we leave the heart, it's an artery. For the most part, we talk about your systemic circuit when we talk about those. And so we talk oxygenated blood in your arteries, deoxygenated blood in your veins. But keep in mind that your pulmonary circuit is the opposite. All right. So the deoxygenated blood is going to go through your pulmonary arteries because it needs to go to your lungs to pick up the oxygen. When that oxygenated blood comes back, it still comes through veins, but those are your pulmonary veins. So just be careful with that. Sometimes that gets a little tricky for kids because you kind of learned probably somewhere along the way artery, oxygen, vein, lack of oxygen. And that is true for your systemic circuit, but your pulmonary circuit is backwards. So kind of retrain your brain. Veins come to the heart, arteries go away, and it doesn't necessarily have a connection to who has oxygen and who doesn't. Okay, so just something I was thinking about, so be careful with that. Moving down into your left ventricle, this is the strongest chamber of your heart. You've got really thick papillary muscle here, really thick chordae tendineae as well, and just the overall lining of the myocardium here is considerably thicker as well, and it needs to be, right? This is going to be the chamber that ultimately pumps and pushes blood out into your body. And so rather than just going to the lungs, which is a relatively short distance for that right ventricle to push blood to, your left ventricle has to make sure that it is capable of maintaining blood pressure so that the blood gets all the way down to your feet, all the way up to your head, and all the way back to your heart. So we are going to push that blood through your aorta. So another opening here is also your aortic semilunar valve. And then you also have your entrance to your coronary arteries here as well. So those arteries will then go out and feed your heart before they get circled back to the coronary sinus and back into your your right atrium as well.